Thank you, Mattia. Good morning. So thanks for coming to listen to my talk. So in short, the talk is on transcranial magnetic stimulation. It's a technique that can be used for many things, but the long title is Magnetic Neuromodulation, a non-invasive and safe treatment for various brain disorders. So Mattia has already introduced me. I have few affiliations here. I have to wear all these three hats in order to do research in this area. So the structure of my talk is as follows. So first I'm going to tell you what is transcranial magnetic stimulation and why is it important. And then I'm going to talk about how complex is the brain and how we use different techniques to study the brain and change some functionalities in the brain. And then I'll talk about neuronal circuits, and then I'll show you some animal studies that we did, and then I'll talk about another aspect of our research, which is combination of TMS and another technique called as deep brain stimulation, which of course is a competitive technique, but I'm going to make a case that TMS is better than the deep brain stimulation. And then I'm going to talk about brain phantoms, how we have made a replica of the brain that mimics the structurally and also in terms of electrical properties. So why is neuromodulation important? So to understand that, we have to know a little bit about brain. So for a very long time, brain has been considered as a chemical organ. If you wanted to change any functionalities of brain, you would take drugs to overcome some of the disorders. But for a very long time, clinicians forgot that brain is actually an electrical organ. It can be considered as both electrochemical organ, so but the electrical part is ignored. It is if you consider electrical part of the brain, you can do many things without having to affect the other parts of the brain, other parts of the human body. And also, an adult brain has about 100 billion neurons, each connecting to 10,000 other neurons. So if you think of number of connections, so they are more than the number of stars in our galaxy. So if you want to study the brain, you have to study each of these connections, because each of these connections affect some part of your life. So it's a very complex research if you want to study the brain or modulate the brain. And moreover, in the US alone, 1 in 4 or 5 people above the age of 18 suffer from a diagnosable neurological disorder. So that's a large number. So if the population of US is about 300 million, so 1/4 of or 1/5 of the population suffers from a diagnosable neurological disorder. That means there is a critical need to come up with some treatment procedures that are effective and non-invasive, not like the drugs that you take or surgery or ionizing radiation. They have to be non-invasive and still be effective. So there is a critical need. That's why not just the US government, various governments all over the world are pouring in a lot of funds to enhance research in neuroscience or neural engineering. So probably you are all aware of the European Human Brain Project that started in 2013. It has an estimated budget of 1.61 billion US dollars. And US also is estimated to spend about $4.5 billion over next 5 years in neuroscience or neural engineering. So there's a lot of funding that's coming towards brain that shows why this research is so important. So I'm making a case that transcranial magnetic stimulation, which is also called TMS or RTMS, is a technique that can be used for treating many neurological disorders. That's why it's an important technique. So what is transcranial magnetic stimulation? Basically, it's a technique which uses short pulses of magnetic field. So we use a magnetic coil and apply short pulses of magnetic field on the region where we want to stimulate. So when you have a time varying magnetic field that is minus dB by dt, you can induce an electric field in any conductive parts of the brain. So that is by Faraday's law of induction. So that means you can use time varying magnetic field in a coil and induce certain electric field. You have to do it precisely on the region of the brain where you want to stimulate, or where there is certain disorder. So it sounds very simple, but it's not very easy to be very focal or to stimulate deeper regions of the brain. So when you induce an electric field, that electric field has to overcome an action potential. So the neurons, they rest at a potential which is called the resting potential, which is about minus 70 millivolts. So if you cross minus 55 millivolts, then neurons fire. So you have to induce an electric field that can go to this threshold. Once you cross this threshold, neurons fire. So that firing is an excitation of that neuron. So that means you can initiate an action in that part of the brain if you cross this threshold potential. So we use sufficient field to induce an electric field that can cross this barrier and excite those neurons. We can also inhibit neurons by doing the opposite. So that means you can excite or inhibit neurons by using a time varying magnetic field. And this can be done completely non-invasively, and it is safe because you don't have any contact, it doesn't need any ionizing radiation, or it doesn't need any surgery. So for that, you need a stimulator that can produce time varying magnetic field. These magnetic fields are large, so you need a capacitor that can store the current and then discharge in this coil. And because there is a large current involved, you need some SCR or a thyristor to control the triggering. So when you trigger, so when you send the current to the TMS coil, it generates a time varying magnetic field which is of certain frequency. We use 2.4 kilohertz. I'll give the details in the next slide. And that time varying magnetic field will induce a time varying electric field, which is in red graph. So there is a phase lag between them. So the currents used in the coil are of the order of 5,000 amps and at a frequency of 2.5 kilohertz. So it's a very short pulse of 0.4 milliseconds. So when you use such a signal, the magnetic field generated, of course, it depends on the number of turns in this coil. So if you measure the magnetic field on the surface of the coil, it's about 1.5 Tesla, but it's a short pulse. So if we repeat these pulses 10 times a second, so if the repetition rate is 10 hertz on somebody's brain at the left dorsolateral prefrontal cortex, that is nothing but your executive part of the brain. If anybody has a depression, and if you stimulate 10 hertz on their executive part of the brain for 5 days a week for 2 months, every day, an hour of stimulation, which is about 3,000 pulses per session, if you do that for 2 months, it induces permanent changes in the brain. That permanent change treats the depression. So that means without taking any drugs or without having surgery or without any ionizing radiation, you can just use these pulses to have permanent changes in your brain that can treat depression. So that is very attractive. If you go to any major hospitals in the US, each psychiatry division will have this TMS device. So it is becoming very popular, not just hospitals. There are TMS centers coming up in the US. That's because it's non-invasive and you don't need a full-fledged hospital for that. You can get this treatment in an outpatient setting, meaning a doctor can prescribe, a nurse can put these pulses for an hour every day for 2 months, 5 days a week, and you can have a cure for depression. So that's why it's becoming very popular. But what we are trying to do is trying to use this technique to treat other disorders like Parkinson's, Alzheimer's, obsessive compulsive disorder, and PTSD. So that is the goal. So for depression, it's already proven. That's one of the big motivation. So here is a video that shows some of the capabilities of TMS.
That could control your brain. To find out if such a thing could actually work, I offered my own brain for a test. It seemed like fun at the time.
Hold it up, you can look at it.
Psychiatrist and neurologist Mark George said he could make my thumb twitch.
Jeez, it does. Oh, that was nice.
Using a map of the brain, he can zap the area that controls a specific body part, like my toe.
Oh, wow.
Is that last stroke a little too much?
A little bit, yeah, it was a little much.
1, 2, 3, 4.
The wand can even affect someone's speech.
10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20.
And once the pulse is removed,
25, 26.
everything goes back to normal.
29, 30.
It's sort of a remarkable thing that one can put something over somebody's head and modify the way they behave.
Wow. The wand works by producing a powerful magnetic pulse.
So it doesn't look like a lot, but the magnetic field that it generates is about the strength of an MRI machine, of a very strong MRI machine.
Since electricity and magnetism are really just two forms of the same thing, a magnet can affect the electrical signals in your brain. Now this is your brain. It's basically an electric web of billions of neurons wired together. When a strong magnetic pulse hits these neurons, it alters their electric current. The process is called transcranial magnetic stimulation, or TMS.
Electricity is the currency of the brain. All thoughts, all beliefs, all actions are just electrical impulses. And so TMS, we're actually able to get in there and influence the currency of the brain focally and non-invasively.
The stronger the magnetic pulse, the deeper into the brain it goes. And by adjusting the pattern of the pulse, you can change the way that part of the brain functions.
We can turn a part of the brain up or down or temporarily turn it off. It doesn't take a genius to see that it should be a pretty fertile way to begin to understand how the brain works.
Okay, so so the two people who you saw, one was Mark George, and Mark George is from South Carolina University, and Alvaro Pascalione, he's from Harvard Medical School. These were the two people who are responsible for making TMS so popular in the US. I think it's also becoming popular everywhere else. So it was originally tried or tested for depression, but right now it's FDA approved for 3 major disorders, which is depression, OCD, and migraines. So there are several, it was only one company before that was FDA approved. Now there are 3 companies, Neuronetics, Brainsway, and MagVenture, that are FDA approved for depression. And for migraine, there is another small company called eNeura. Brainsway also has been FDA approved for OCD. So apart from these are the treatments that are available for public. You can go pay for it, or your insurance can pay for it, and you can get the treatment. But there are several open label clinical trials. You name any neurological disorder, there is some group in the world which has tried TMS to treat that disorder using TMS. So it is becoming very popular. Everybody is trying to use TMS to treat one or the other disorder, but using the same commercial setup. So why is it so popular? Because it has several advantages, as I already said. It's non-invasive, safe, inexpensive, because it can be done in outpatient setting, and it is target specific. So what are the disadvantages then? It is currently limited to cortical stimulation alone. If you want to stimulate deeper parts of the brain, of course you have to pump in more current in your coil. But if you pump in more current, you end up stimulating the cortex more to stimulate the deeper regions. You don't want to overstimulate the surface in order to stimulate the deeper parts. So that's not the right approach. So that's why it's now restricted to just the cortex. And then it produces clicking sound. Some patients might find it annoying. And then the coils heat up because there is 5,000 amps current for a very short time. Though it's very short time, but if you stimulate for longer durations, the coils can heat up fairly quickly. So the stimulation profile or the induced electric field in the brain depends on the coil shape, size, and number of turns inside. So if you have more number of turns, you can have higher magnetic field, but then if you have more number of turns, you also increase their impedance and so on and so forth. There are limited types of coils available in the market. These two were very popular for a very long time. This is single coil and this is double coil. Double coil has 2 types of windings that meet here. So at the center, you get an addition of currents which leads to a peak at the center here. So this is more focal compared to this coil. So the current commercial coils look like this. They're slightly more complex. This is Neurostar coil. There is some ferromagnetic core here, but not at the surface, because you don't want to have a ferromagnetic core that has a saturation magnetization of less than 1.5 Tesla, right? Because you want to have higher and higher fields. If you have any ferromagnetic core, they have a saturation magnetization, so that will block the higher magnetic fields. So you don't want to have a ferromagnetic core at the surface here. So there is a ferromagnetic core somewhere else. They don't disclose the design of this coil. This is another coil, slightly more complex. It's called Brainsway's coil. So with this coil, you can stimulate deeper regions. That's because you have so many coils that produce high magnetic field, so you can go deeper, but at the cost of focality. You don't get the specificity needed, so you end up stimulating larger parts of the brain with this kind of coil. So when I was at Cardiff, Dr. Giles's group came up with another coil called the halo coil. So basically, halo coil, the main advantage of halo coil was that it can use the same current as, or same field as the circular coil, and it can reduce the decay rate by using this halo coil. So if you have a smaller decay rate, that means you can stimulate the deeper regions of the brain with less cortical field. So this was one of the advantages of the halo coil, but there is this coil that is right in front of your eye and nose. So when we looked at head modeling, we saw that it was stimulating the olfactory nerve that I haven't shown here, but in terms of the field and the induced in terms of the magnetic field, if you look at 10 centimeter deep, that is 0.1 meter here, this is the halo coil setup, and this is just a single coil. So you can see that the halo coil has much higher field at a deeper region of the brain for the same surface field. So so that was one of the advantage. But the disadvantage was it was stimulating the olfactory nerve and the optical nerve. So we, when I started to work in his group at Iowa State, we came up with a modified version of halo coil called triple halo coil. So basically what we did was we used two other halo coils in order to reduce the field that on the nose where you have the olfactory nerve and also the optical nerve near the eye. So you can see here this region is not affected much because there are these coils that have currents running through them in opposite direction. So this is the result of the magnetic field. If you look at different depths from the top, so at 10 centimeter deep from the top, you can see that this is the triple halo coil, and halo coil is this one, and this is figure of 8 and circular coil somewhere here at the bottom. So you can reduce the decay rate even further when you use triple halo coil and reduce the stimulation on the olfactory nerve. So this is another design. So both the halo coil and triple halo coils were designed to stimulate deeper regions of the brain for the same stimulation on the cortex. But what if you want to stimulate really small area on the surface of the brain itself? There is no coil in the market that can do that. For example, if you want to treat schizophrenia patients, they hear voices that are due to malfunctioning of primary auditory cortex. Primary auditory cortex is a very small region in the brain that lies on the surface. So if you want to stimulate only the primary auditory cortex, you need to have much higher focality than the existing double, that is figure of 8 coil. So we proposed a modified version of the double coil. So basically we have another small coil here, and the double coil has a tilt to it, and then we also put 2 shielding materials here of permalloy. So by using this configuration, we can increase the focality that is sufficient to stimulate smaller regions like primary auditory cortex. So this is another design that we are planning to fabricate soon. So there are these different designs of coils, but how do we say that, okay, this can stimulate deeper or this has more focality? So we do that by calculating magnetic field and induced electric field in the brain. So that means we need to have a good brain model. So how do we get a good brain model? You can't just have a this is called standard anthropomorphic model, which is homogeneous. It has one electrical conductivity, one permittivity, and permeability. Most of the content of the brain or layers of the brain are non-magnetic, so we take it as one. But their conductivity varies drastically. So this is not a good design. So that means you have to take MRI images of a patient and then look at different regions and assign different electrical properties to each region based on the literature. There are many people who have reported electrical conductivity of different parts of the brain. So when you get an MRI image, doctors can say which region is what, but how do you segment it? How do you assign that certain electrical conductivity to different regions? That is a complex procedure. So we use several techniques to segment each region in the brain from an MRI, and then assign electrical conductivity to each brain. So the resultant model looks something like this. So it has all the brain regions. It has skin, skull, gray matter, white matter, CSF, is cerebrospinal fluid, and so on and so forth. It has about 50 different regions in there. Each have different electrical conductivity and permittivity. And we are using permeability as one. So when we have such a good head model, then we are able to calculate the induced electric field from different coil designs accurately. So that is very important, because if you don't consider that, if you look at 2 head models here, one is a head model of a small child and another is an adult. So if you use a standard anthropomorphic head model, you don't see significant difference between the induced electric field between these 2 head models. Whereas if you use the heterogeneous head model and calculate the induced electric field, you can see that there is significant variation. So this is using standard anthropomorphic head model, and this is using heterogeneous head model. So it is important to use heterogeneous head model because there is large variation in different structures. You can't just, for example, you can't just take a dosage for an adult and scale it down for a child if you want to treat a child with TMS. So we have developed lots of head models for different patients as well. The healthy head models, these 50 healthy head models that we have developed, we have licensed to a company called Zurich MedTech. So you can use them for free if you are using for research, but if you are using for commercial purpose, you have to pay a certain amount of fees. And we have several other head models which are not licensed yet, but we have it in our database. We need different head models because different, if people have different disorders, their electrical properties can change, and sometimes the magnetic properties can also change. For example, people with Alzheimer's have ferritin accumulation in their brain, and if there is ferritin in their brain, obviously the magnetic permeability will be different for their head models. So it is important to have head model specific to certain disorder that you are studying or specific to certain patient that you are studying. So this is all about the modeling, but there is very little work at the cell level. So what happens when you apply a magnetic field on a single neuron? There is not a lot of study because TMS was approved because it was non-invasive. It was approved quite quickly in its conception. So not many people have studied the mechanism at the cellular level. So we thought we should look at what happens to the cell morphology, cell growth when you use TMS on certain neurons. So we used a kind of neurons called N27 neurons. These are dopamine producing neurons. They are deep inside your brain in an area called substantia nigra. So these are responsible, the death of these neurons will result in Parkinson's disease. So that's why we wanted to look at these neurons when we apply TMS fields. So we grew the neurons in these T75 flasks and applied magnetic field. So in one flask, the field is into the plane here and outside coming out of the plane here, and it's vice versa on the other side. So what that does is it induces eddy currents, or the induced electric field will generate currents in clockwise and counterclockwise in these two loops. So that means we are growing neurons that have eddy currents in clockwise in opposite directions. What that does is, we don't know why exactly, but somehow the currents in clockwise and counterclockwise direction is producing differential growth rate. So the one that is field up is accelerating the growth, and field down is decelerating the growth of the neurons. The neurons grow at a slower pace if the field is down, and if the field is up, the neurons are growing at a accelerated rate. We also looked at, I did not put the latest work, we also looked at the axonal length, the soma area, and so forth. And we have got similar results, that one direction of the field enhances the growth and another one decelerates the growth. So why are these results important? So that means if you can design a coil that can stimulate the substantia nigra area, the deeper structure that produces these cells, with well-designed direction of the field, you can control the growth rate. If the cells have died, you can make the other cells grow, and you can also use the same technique to decelerate the growth of certain cancerous cells. So that was about the cell morphology and the growth. But what about the functionality of the neuron? So the neurons fire at a certain frequency. So different neurons have different firing rates. So how can we model these firing rates? So in 1966, Hodgkin and Huxley proposed a model which won them Nobel Prize. Their model shows how the neurons fire. Basically, it's a set of transistors and diodes that show the firing rate when you input a certain stimulation to the neuron. So we used the same, a modified version of Hodgkin-Huxley model called integrated fire neuron model, and we induced our TMS equivalent field on them. So, but before that, the neurons, you don't get neurons that are isolated in the brain. Different regions of the brains have different type of neurons, and each neuron, as I said in the beginning, is connected to 10,000 other neurons. So you can't just use one existing model and apply magnetic field and see what is its output, because it's connected to so many other neurons. You have to take into consideration the entire network in order to see how the neurons respond to TMS field. So this is an example of a motor pathway model. So it's when you decide to move your hand, it's a very complex procedure in terms of the signal transmission in the brain. So first, your executive brain says, okay, move, and then the signal doesn't directly go to your spinal cord and you move the hand. It goes to multiple other parts of the brain. Some parts try to decelerate, some parts try to accelerate. So the reflex action for any pain that bypasses the executive part. So it's a very complex model. So though moving in hand is so easy for us, but there is a complex mechanism that is underlying that simple movement of hand. So this is a neuronal model. This is a motor pathway model for any motion. So it starts at the cortex, and then different regions control your motion. So one of the region is your substantia nigra area, and when the dopamine that is produced by substantia nigra is cut off, you get tremors. That's what happens in Parkinson's. The dopamine releasing neurons are dead, so there is lack of dopamine, which disturbs this motor pathway model, and you get tremor. So this is how complex is the model. So we slightly simplified the model because we, each of these regions or nuclei have about 10,000 neurons. We used 10,000 neurons because anything more was making our model really complex, and anything less was not a efficient model. So we used 10,000 neurons per each region, and each of all those 10,000 neurons are connecting to 10,000 other neurons. So we developed this model using those connections, and each of them have certain weights. We developed our model and verified with the firing rate of each of these are already well published in literature. For a healthy model, what should be the firing rate of these nuclei? and what should be the firing rate of this nuclei is all well reported. So once we match firing rate of all of these neurons in our nuclei, then that's our healthy model. So if we remove the dopamine, then the whole network gets disturbed. And that is also well published. When you remove the dopamine, the firing rate of each of these nuclei, the neurons fire at a different rate. And that is well published. So this matches the existing literature. We developed these models. This is without any external stimuli. So if you look at the firing of each region, all these dots indicate firing of a neuron. So each of these regions fire in this way. So this is a healthy model, and if there is a lack of dopamine, you get this type of firing rate, and this is well published in the literature. And this is often quoted that this is, if you see this synchrony is what causes the Parkinson's. So we use for a reliable treatment for Parkinson's nowadays, apart from drugs, is a technique called deep brain stimulation. What they do in that technique is they implant 2 electrodes in the brain and they stimulate the neurons in the substantia nigra area where the dopamine producing neurons are dead. So you have more dopamine release from those neurons, and it's a reliable technique. It's very expensive. Each surgery costs about $100,000 US. It's also risky because you are having an open brain surgery, but it's reliable. Once if you get a chance, you should see a YouTube video on that one. As soon as you turn on DBS electrodes, a person who has tremors like this can immediately stop and become a normal person. It's that effective. So it's an effective treatment, but it's risky and expensive. So what DBS does is basically it increases the number of firing here. Here there are less and there is a synchrony, but it increases the number of firing of this nuclei, which gives you a normal motion. So we use TMS instead of DBS. We use TMS on the cortex. So when we do that, we get firing in GPI in this fashion, which is more than the Parkinson's model, and it has less synchrony. So if you compare that GPI region, healthy looks like that, Parkinson's looks like that, and if you use DBS, it reduces your tremor, it makes your motion normal, but not similar to the healthy one. It doesn't go back to the healthy one. But if you use TMS at 50 hertz, you can see it's closer to the healthy one than the DBS treatment. So this is based on our model and our study. So we have to prove it. So if we have to prove it, first we have to do it in animals. So we collaborate with Department of Neurology, Neurosurgery, and Department of Psychiatry. Department of Neurology is where our animals are housed. But before going to the actual animal study, we have to also do some modeling on the animals to get the accurate stimulator and the coil and so on and so forth. So we have been doing this study for a very long time. We have looked at different coil designs on the animal. So this is using a commercial coil. We have measured the magnetic field generated by a commercial TMS coil for animals. And then we looked at, again, we took a MRI image of a mouse and we developed its head model, and then we assigned electrical properties to it, and we looked at the induced electric field from a commercial coil, which is not good because it ends up stimulating the entire head of the mouse. That's not what we want. We want a coil that can stimulate precise region of the brain. Mouse brain is very small, so it has to stimulate very small area. So we looked at multiple designs of the coil, and it's impossible to come up with a design that can stimulate small area of the brain, of mouse brain, with the field strength that is capable of inducing a action potential. Remember the first graph I showed from minus 70 millivolts to minus 55 millivolts. We have to have that, we have to cross that barrier in order to initiate an action potential. And the amount of field needed for that is quite high. Because the amount of field is high, the coils become bigger. So this is one where we fabricated, but we decided to use a ferromagnetic core for that, because we realized that unlike human brain, if we have to go to human brain, there is a large gap. It's almost 1 centimeter gap before we go to the surface of the brain, whereas mouse do not have that. Mouse have less than 3 millimeter gap. So if that is the case, that means we don't need so high field, which means we can use ferromagnetic core. If we can use ferromagnetic core, that means we can do focal stimulation, because if we can shape a ferromagnetic core in a pinpoint way, we can concentrate the flux. So we developed this mouse coil. We have latest results as well, which I did not have time to put them on. So this is actual animal study using a commercial coil. So basically here, this was our preliminary study to look at what happens to the mouse if we stimulate. We found that it becomes, somehow when the mouse is put in a confined space, it sticks to the walls and goes. This is a motion study using some fancy equipment. So this is all the paths of the mouse. So if you stimulate with TMS, it comes out away from the corners. It doesn't have so much fear, which is due to dopamine and serotonin, changes in dopamine and serotonin levels in the brain. That also we confirmed by looking at the neurochemical analysis of the mouse brain. So when we completed the study, we harvested the brain and did the neurochemical analysis of the brain, and we found that the cortex of the mouse brain had much higher dopamine and serotonin compared to a mouse that did not have TMS stimulation. So because of that, the mouse sheds some of its inhibitions or fear. So that was the animal studies. Currently we are, the work in progress with animal studies is to replicate that complex motor neuronal pathway. So we are working on that. But this is another study that involves DBS. DBS stands for deep brain stimulation. Deep brain stimulation is a technique, as I said, wherein this is a technique for treating Parkinson's patient, wherein 2 electrodes are implanted in the person's brain, and they stimulate near substantia nigra area that reduces the tremor. But eventually patients will get used to those stimulation currents inside the brain, and then they, after about 10 years with these implants in the brain, they start to again get back the tremor, or they will have other impairments like speech. Their speech becomes difficult, or they have speech impairment, they can't speak. So speech originates from motor cortex, and if you want to improve the speech, you have to use TMS because it's right on the motor cortex, but your DBS probes are deep inside. They can't stimulate the cortex. So a neurosurgeon came to us and asked, what happens if I stimulate a Parkinson's patient's brain on the surface if they have DBS implants already? So what is the EM interference between them? So we looked at what happens to the temperature. Are there any forces involved? And what is the induced electric field on the DBS probe due to TMS? So this is the simulation study, modeling study we did, and we concluded that there is not significant change in the temperature, which is here, but there is change in the induced electric field. Not all the time, only when you move your TMS coil right on the top of the DBS electrode. But DBS electrodes are not just a single electrode that or two electrodes that go straight like that. Actually, they have redundant coils that sit on the top of the brain, and each neurosurgeon does it differently. They put these redundant coils in a convenient way wherever possible. So those act as a secondary coil, and they can pick up the induced electric field that is induced from, or they can pick up the field from the TMS coil. So the actual probes are not the concern, but it's the redundant coils that come out of the DBS probe are the actual concern, because they're conductive, they have large induced electric field which goes down to the probe. So that is what we found out, and there is literally no forces. There is no Lorentz force on these probes due to the TMS field, because of the distance, there is very negligible force between them. And when we looked at the temperature on the probes is not that high. And there is a small increase in temperature of 0.5, but that can be ignored. So I think I have another 5 minutes. I will introduce another topic. So we did this modeling, right? But if we want to actually measure the temperature difference or the induced electric field or stimulation strength in DBS due to TMS, we had to measure it in a brain phantom. So how do we make a brain phantom? So we have done a lot of head modeling. As I said, we had a large database of Parkinson's, Alzheimer's, and schizophrenia head models. So we had the data. All we need to do now is to print them with the material that have similar electrical and magnetic. Of course, magnetic is just, you can consider them as non-magnetic and have permeability of 1. But you have to have different conductivity for different layers of the brain or different regions of the brain. So can we build a brain phantom with different conductivity and that mimics the complex structure of the brain? We did that by first 3D printing shells that can be dissolved. Once you fill them with a polymer that has similar conductivity of different layers. So first we established that we can print a brain phantom with anatomical accuracy. meaning we can segment gray matter, white matter, CSF, and all that, those regions accurately. And then we used something called shelling method, wherein we had space to fill a polymer, and we could replicate that polymer. And now we had to make that polymer of certain conductivity. That means we should be able to tune the conductivity of our new polymer. So we came up with a composite polymer of CNT and PDMS. Basically, we mixed CNT in PDMS in different proportions to give us a known conductivity. So if we want certain conductivity, we can mix that amount of CNT and get different conductivity. So this is where the white matter and gray matter is somewhere nearby, but CSF has high conductivity, which is around this area, so which needs high CNT percent for CSF. So we verified the anatomical accuracy as well as conductivity. So this is a brain phantom that is made from the new composite material of CNT and PDMS. It has a conductivity similar to our brain, and the accuracy is confirmed by taking the CT scan of these phantoms and matching them with the original MRI images. So now, if we use that brain phantom on a TMS coil, we get these similar results, wherein for different depths, you get different stimulation strengths. We haven't confirmed this with actual people. So to conclude, I think transcranial magnetic stimulation is a promising technique. You can excite and inhibit any part of the brain, in order to understand its mechanism properly, you need to do more cell culture studies and also animal studies. And there is a lot of scope to develop new neuronal circuit modeling for not just motor pathway, but for memory, for other tasks as well. So, and we developed a anatomically realistic brain phantom that can be used to test stimulation strengths from a patient. So I'd like to thank all the people who have contributed to this work. So this is my group. So these are all my students. So this is how we started, and now currently these are the people I have, and we are funded by these 3 funding agencies. I'm happy to take any questions you have. Thank you. So on the surface of the coil, you can get up to 1.5 Tesla. 0.5 Tesla, 1.5, yeah, on the surface of the coil. But as you go down, by the time you reach the surface of the brain, you have less than 0.3 Tesla for human. Again, it varies for different people. As you grow older, the brain shrinks a little bit, and older people will need higher current in order to initiate the same action potential in the neurons. So the Parkinson's disease is a complex disease. It originates from the deeper region in the brain where due to the death of dopaminergic neurons in substantia nigra, and then it affects the entire circuitry. There are multiple components that are involved in the motor pathway. So when the dopamine is taken out, your M1, the primary motor cortex, becomes very active, and that's what leads to the tremor. So there are multiple ways you can control the tremor. One is by correcting the entire circuitry, or by controlling the nerve that goes to goes to your different limbs. But then you will have to have multiple controlling mechanisms to control the. So, sorry, I did not understand. Yeah. Yeah. Yeah, probably, yeah. But if you know what are the interactions between the DBS probe and the TMS, then you can adopt a protocol which is safe. Yeah. Yeah. So just because the distance between if you calculate the Lorentz force between the probe and the coil, though the magnetic field on the coil is high, the field on the DBS probe is very low, so there is very little interaction in terms of force.
Surprised by the fact that, as you said at the beginning, it's permanent, the effect on the pressure.
Mm-hmm.
You said that it creates permanent change
Yes.
in the brain.
Yes.
So I was wondering if this applies also for Parkinson. I mean, do you expect, or you are already able to do it, to change the production of dopamine in such a way that it's permanent, it doesn't require the patient to be treated continuously? Because that would be definitely a huge breakthrough.
Yeah. So in order to have permanent effects, what we need to do is generate more dopaminergic cells. That will lead to the permanent change in the brain, right? But it's not easy to generate so many neurons, new neurons. And also it's deep inside the brain, so there is not much study. Maybe somebody will come up and say, yes, we saw the permanent change. But to do that, you have to stimulate that deeper region without affecting other regions, which is very complex.
So far, at the state of the art, how long does the effect last?
For depression?
No, for the Parkinson effect.
Parkinson, we
Only some masses.
yeah, we have only done it on that too. Not, I mean, that's the modeling study where we have shown that okay, if you use 50 hertz TMS on the cortex, you can bring back the circuitry to the normal. Currently we are testing that model in mice. We still we are not there yet. So we had to stimulate focally for that.
First of all, thanks a lot for very nice and interesting talk.
A pleasure.
And let me have a bit nasty question.
Sure.
You mentioned a couple of times it's completely safe.
The TMS for depression. Yeah.
From the mechanism you described, how it works, I would say it's potentially very dangerous, and if you know how to apply, you can totally cripple the patient or person. Did it ever happen, or were there any negative
Yes.
effects or side effects observed?
Yeah. So, side effects, no, but adverse effects. So when you are treating patients, because it has existed since 2008, so a lot of people have undergone this treatment, and if there are many people, of course, there will be some adverse effects. Adverse effects are something that happens because of some abnormalities. Whereas side effects, there is, for side effects, to study side effects, you need more time. So far, no side effects in this short time. But the adverse effects, some people, for example, older people, because they have larger skull to brain distance, because their brain shrinks a little, you need to crank up the current in your coil in order to get that action potential. So that means you are stimulating larger area as well when you crank up the current in the coil. So when you stimulate larger area of the brain, you are going beyond motor cortex to other surrounding areas. When you do that, that induces seizures. And there are cases where people had seizures because of their anatomy or the dosage. And seizures are not very serious. So when people undergo seizure and then come back, and it's reversible. Actually, some seizures are good. People used to earlier induce seizure to treat depression. Yeah. 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 So that's with our modeling studies. So we don't know what happens in actual sense. So this is a new coil design that we wanted to look at. So in our simulations, we saw that there is huge induced electric field on the olfactory region and the optical region with that new coil design of halo coil. So that's why we came up with a modified coil design called triple halo coil. Yeah.
Thank you once more for the lecture.
Thank you for your time. Thanks.